Look around the room you are in right now. The floor beneath you, the foundations below it, the columns holding everything up there is a good chance that most of it is made from concrete. Now imagine being told that one of the most promising ways to improve this material does not require a new chemical, an exotic mineral, or some futuristic form of carbon capture. It requires a very large press. Researchers in China have been experimenting with a process called compression casting. They take ordinary concrete while it is still wet, place it inside a reinforced mold, and squeeze it under enormous pressure for several minutes. The ingredients do not fundamentally change, but the material that comes out can be dramatically denser and, in some laboratory tests, more than twice as strong. That sounds almost too simple, and that is exactly why it matters. Because concrete is not some niche material that can be replaced overnight. It is the physical foundation of the modern world. Humanity uses more concrete than any other manufactured material. By mass, only water is consumed in greater quantities. And the ingredient that holds concrete together, cement, is responsible for roughly 7 to 8% of global carbon dioxide emissions. So even a modest improvement to the way concrete is manufactured could have consequences on a planetary scale. But before calling this a revolution, we need to answer 3 questions. Why does squeezing wet concrete make such a large difference? How much carbon could it realistically save? And why are we not already using it everywhere? Concrete looks simple from the outside. Mix cement with water, sand, and stone. Pour it into a mold. Wait for it to harden. But inside that wet mixture, an extremely complicated process is taking place. Cement reacts with water and begins forming a hardened network around the grains of sand and stone. That network eventually gives concrete its strength. The problem is that ordinary concrete contains more water than the chemical reaction strictly needs. Some of that extra water is necessary because builders need the mix to remain workable. Concrete has to flow through pumps, around reinforcing bars, and into every corner of a mold. But once the concrete begins to harden, much of that water is no longer useful. It evaporates or migrates out of the material, leaving microscopic spaces behind. Air trapped during mixing creates even more spaces. Engineers call these spaces pores, or voids. And although most of them are too small to see, they influence almost everything that happens to concrete later. Water penetrates through them. Salt travels through them. During winter, water inside them can freeze and expand. And when corrosive chemicals eventually reach the reinforcing steel inside a structure, that steel can begin rusting and expanding, slowly cracking the concrete from within. There is another weak point. Around every piece of stone aggregate is a microscopic boundary where the stone meets the cement paste. Engineers call this the interfacial transition zone. In conventional concrete, this boundary is often more porous than the material on either side of it. That makes it a natural starting point for cracks. For decades, engineers have tried to improve these weaknesses by changing the recipe using chemical admixtures, supplementary cementitious materials, alternative binders, or much lower water to cement ratios. Compression casting approaches the problem differently. Instead of asking what else should be added, it asks what can be physically removed. The process begins like normal concrete production. The cement, aggregate, and water are mixed together and placed inside a specially reinforced mold. Then pressure is applied while the mixture is still fresh. In the research published so far, pressures above 5 megapascals have commonly been maintained for roughly 2 to 5 minutes. For perspective, this is not someone pushing down on a mold with a heavy weight. It requires industrial hydraulic equipment and molds strong enough to resist forces that would destroy ordinary formwork. As the pressure rises, something visible begins to happen. Excess water is forced toward the edges. Trapped air escapes. The loose particles inside the mixture are pushed into a much tighter arrangement. The concrete physically becomes more compact before it has even begun to harden. Think of the difference between pouring sand into a container and pressing that sand into a dense block. The ingredients are the same. Their internal arrangement is not. A 2024 study examining compression cast concrete under pressures of 5, 10, and 15 megapascals reported compressive strength increases ranging from approximately 55 to 122%, depending on the mixture. The same study found that increasing the casting pressure substantially reduced porosity and made it much more difficult for carbon dioxide to penetrate the concrete. Other studies have reported better resistance to water absorption, freeze-thaw damage, and chemical attack. The explanation is not mysterious. Fewer large pores mean fewer pathways for water and corrosive chemicals. A denser transition zone means cracks have a harder time finding a weak place to begin, and a tighter internal structure allows the concrete to carry more load before it fails. The surprising part is that the researchers achieved these improvements without relying on an expensive new additive. They changed the manufacturing process, not the fundamental recipe. But this is where the story becomes more complicated. Compression casting does not stop cement from releasing carbon dioxide. To manufacture Portland cement, limestone is heated to temperatures of roughly 1450 degrees Celsius. Part of the carbon comes from the fuel needed to reach that temperature. But a large share comes directly from the limestone itself as it chemically decomposes. Even a kiln powered entirely by low-carbon electricity would still release process emissions. Compression casting attacks the problem indirectly. If a smaller quantity of cement can produce concrete with the same required strength, less cement may be needed for a given component. Alternatively, manufacturers may be able to use lower quality or recycled aggregates without accepting the usual reduction in performance. Researchers have already tested compression casting with materials including recycled concrete aggregate, waste rubber, desert sand, and recycled powders. In other words, the process does not make cement carbon-free. It may allow engineers to get more structural performance from each kilogram of cement they use. A life cycle assessment published in 2024 estimated that compression casting could reduce carbon emissions per unit of compressive strength by roughly 21 to 45% compared with conventionally cast concrete. The same research modeled several hypothetical adoption scenarios. Under those models, replacing 25% of conventional concrete component production with compression casting could reduce annual emissions from the global concrete industry by around 7%. At complete adoption, the modeled reduction reached 27%. Those are not measured global savings. They are projections based on life cycle models, assumed adoption rates, and specific concrete mixtures. But even the lower end is significant for an industry this large, and it helps explain why the research is attracting attention. The important word, however, is could. Because there is a major difference between producing an impressive cylinder in a laboratory and safely manufacturing millions of structural components. The easiest way to describe compression casting is to say that we should simply press all wet concrete before it hardens. In practice, that is not possible. Most concrete is delivered to construction sites in mixer trucks and poured into columns, foundations, walls, or slabs. You cannot place an entire building inside a hydraulic press. Compression casting is currently most practical for precast construction. These are components such as beams, wall panels, pipes, sleepers, and floor slabs that are manufactured inside a factory and then transported to the building site. A factory can install permanent presses, control the mixture precisely, and reuse reinforced molds thousands of times. A construction crew pouring a foundation in the middle of a city cannot. The molds themselves are another challenge. Ordinary formwork only needs to hold wet concrete in place. Compression casting molds must survive several megapascals of pressure without deforming. Different component shapes may require different molds, increasing capital costs and limiting flexibility. Then there is brittleness. High compressive strength sounds universally positive, but stronger concrete can also fail more suddenly. Researchers studying compression cast concrete have specifically warned that normal design rules may not always apply. Some applications may require additional steel fibers, confinement, or changes to reinforcement design. And before any new structural process can be widely adopted, engineers need long-duration testing. What happens after 20 years? How does the material behave in a real bridge exposed to salt, vibration, and changing temperatures? Can every factory reproduce the same result consistently? What happens when the press is misaligned? The mixture varies, or water cannot escape evenly. These questions are not arguments against the technology. They are the difference between a promising material and a trusted construction system. Concrete standards move slowly because failure is not an inconvenience. It can kill people. Compression casting is one way to rethink concrete. Another Chinese company is asking whether some structural elements need concrete at all. Broad Group has developed a system known as B-Core. A B-Core panel is built from two thin stainless steel plates separated by an internal array of steel tubes. Instead of relying on a thick mass of material, the panel distributes forces through its internal geometry. The principle resembles lightweight structures used in ships and aircraft. Place material where it carries the most stress and remove it from places where it does not. Broad claims that its panels can be many times lighter than reinforced concrete slabs of similar dimensions. Because the panels are manufactured in a factory, they can arrive at a construction site with much of the building already integrated into modular sections. Arrive at a construction site. In June 2021, Broad demonstrated the system by assembling a 10-story apartment building in Changsha in 28 hours and 45 minutes. That number needs context. The modules had already been manufactured before arriving at the site. The demonstration measured assembly time, not the complete process from raw steel to finished building. It also came from the company selling the system. Independent certification, fire performance, full life cycle costs, corrosion behavior and long-term maintenance remain essential considerations. Still, the demonstration revealed a different approach to the same problem. Compression casting tries to make the concrete we continue using perform better. B-Core tries to remove concrete from some parts of a building entirely. These are not one combined technology. They are two separate bets on the future of construction. And both bets begin inside a factory. For most of modern history, buildings have been treated as enormous one-off projects. Materials arrive at the site. Workers cut, pour, weld, and assemble them in changing weather conditions. Quality depends on thousands of actions performed by different people in a temporary workplace. Industries such as automotive manufacturing moved in the opposite direction long ago. They shifted work into controlled factories, where machines can repeat the same process with much greater precision. Compression casting makes sense in that environment. So do modular steel panels. The deeper transformation may not be a single miracle material replacing concrete. It may be construction slowly becoming a manufacturing industry. More components could be produced under controlled conditions, tested before delivery, and assembled rapidly on site. That could reduce waste, improve consistency, and make advanced processes easier to automate. But it also introduces new risks. Factories require large investments. Standardized components can limit architectural flexibility. Transporting large modules is difficult, and concentrating production in a small number of companies could make housing and infrastructure dependent on proprietary systems. Every advantage creates a new trade-off. The numbers that researchers attach to the potential scale of CCC adoption are almost hard to believe until you remember how much concrete the world pours. Life cycle models suggest that switching just 30% of new structural concrete worldwide to the compression casting process could cut annual carbon dioxide emissions by around 850 million tons. To put that in perspective, that is more than the entire country of Germany produces in a year, from every power plant, every factory, every car, and every farm combined. One process change applied to less than a third of global concrete output, delivering that kind of climate result. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets difficult. Building codes in most countries are updated on timescales measured in years, sometimes decades. They move slowly by design because the cost of a structural failure is not just financial. Every country that wants to adopt CCC at scale needs its own independent testing to verify the results under local conditions, its own regulatory approval process, and its own trained workforce that understands how to operate compression casting equipment consistently and correctly. China can share the blueprints, but the rest of the world has to do the work of adapting them locally. There is also the question of infrastructure. Compression casting requires equipment that most concrete plants do not currently have. Retrofitting existing facilities or building new ones represents significant capital investment. For large construction companies in wealthy countries, that investment may pay off quickly given the cost and regulatory savings. For smaller contractors and builders in developing economies, the barrier may be much higher, which raises real questions about whether this technology reaches the parts of the world that need affordable, lower carbon construction the most. None of these challenges change the underlying reality of what the science shows. They simply define the gap between what is technically possible and what will actually happen at scale. Closing that gap is a policy challenge, an investment challenge, and a coordination challenge as much as a technical one. The researchers who published this work in 2025 gave the world a tool. Whether the world picks it up and uses it at the speed the climate situation demands is a separate question entirely. What is clear is that, for the first time in a very long time, the fundamental process of making and using concrete is actually changing. Not just at the margins, not just in a laboratory, but in real structures that real people are using right now. That is new. And given that concrete is the second most consumed substance on Earth, with only water ahead of it, changes to how it is made do not stay small for long. If this video changed how you think about something you walk on and live inside every single day, give it a like and subscribe for more videos about the technologies quietly reshaping the world. Turn on notifications so you never miss one. And I want to hear from you in the comments. If a process change this significant has been sitting right in front of engineers for decades, what other obvious breakthroughs do you think are hiding in plain sight right now?